All right, sorry I couldn't be in class today. Got my first dose of the vaccine yesterday, and I ended up with all the classic side effects, which is just wonderful. But I'm happy to have got my first dose, so on my way to hopefully some reasonable amount of normalcy. So anyway, all right. So I think we're just ready to go. I can't think of anything we need to discuss beforehand. So let me get rolling here. So you'll forgive me if I'm not my usual spunky professorial self today. If I'm a little, fading along the way, I'll be fine, but just bear with me. And unfortunately, that goes along with probably, maybe, probably, this might be the most confusing lecture of the semester. So I warned you about all the jargon in linear programming and the complexity that arises in linear programming problems. And so we're going to see that kind of full force today. I'll try to walk us through it. Don't expect, don't pressure yourself to understand all of this, all the details right away. Just focus on kind of getting the big picture to start with, the overall approach and the main methods and variables and names. And then as you go through this later on and you study it and you do problems for the problem set, it'll start to come together. And it turns out not to be that difficult, excuse me, not that difficult to actually do. It's just that, again, a lot of terminology, a lot of variables flying around will introduce even more variables and things can get out of hand pretty quick. So you remember last time we did this train car example. So we had two trains and we wanted to determine how many cars should be pulled by each of the two trains, X1 and X2. And we found that there were two possible feasible points, two possible solutions in the feasible plane that could, well, they were feasible solutions. And clearly this one, point B, was the one that minimized the total cost. So we'll come back to that problem. We'll look at it in a more general fashion as we discuss the techniques that we'll be using in carrying these out. So I've been hinting at this, but let's kind of nail it down more specifically. So when we're solving practical optimization problems, and by that it just means optimization problems that you would see in industry or in larger scale settings where you're trying to solve real problems, the number of design variables, those are the X's, can get quite large. The number of constraints can also get quite large. They can be in the tens, the hundreds, the thousands, even the millions in some cases. So obviously we're not going to be able to, as we did for the train car example, draw a graphical feasible space. So we're going to have to use our imaginations. We're going to have to use our imaginations in order to kind of develop some sort of analogous picture for these bigger problems. And we're also going to need a more algorithmic approach to finding the optimal solution. So in the previous example, you'll notice what we did was we applied all of the constraints that gave us the feasible space, which turned out to be just a straight line. And we knew that the optimal solution had to be a point on the end of that straight line. So there was only two possibilities. We just brute force checked the value of J, the cost for a train at each point, and found the one that was smaller. So that worked fine for a small number of possible points. Now, again, we could have tens, hundreds, thousands of these points. And so we need a more algorithmic or a more step-by-step approach to doing this. Now, I'm not going to give you all the details of that process, of that algorithm, but what we're leading up to is what's called the simplex method. And what I want to give you is enough information about the simplex method to understand basically how it works, essentially what it's doing, but not enough detail that you could actually program it yourself. These linear optimization codes are many thousands of lines long. There's many situations that you have to allow for, check for, accommodate for. So this is just something I want you to feel comfortable with, basically how to set them up and then what's going on under the hood when you use, in this case, the simplex method. So the first step, which I mentioned on Tuesday, was we need to turn our inequality constraints into equality constraints. And that will allow us then to write everything as just big systems of equations, which we know how to handle. So let's tackle that. That's done using what are called slack variables. And they are exactly what they sound like. So we're going to take our inequality constraint. We're going to add an additional variable called a slack variable. It'll be S for slack, obviously. And that's going to take up the slack in the inequality in a way that I'll show you. So this is all in order to get the standard form of the linear programming problem. So if you remember everything that we had last time, we had the objective or cost function, we had the linear equality constraints, we had the linear inequality constraints, and we had the positivity constraints. In the standard form, we do not have inequality constraints. We only have equality ones. So we need to convert all of our inequality constraints and replace them with equivalent equality constraints. So it's actually quite simple. Again, it seems confusing at first because we're adding in new variables, but it actually is quite straightforward. So let's say we have an inequality constraint that looks like this. So x1 plus 2x2 is less than or equal to 5. All right, so that means whatever x1 and x2 are, when you add 1 times x1 plus 2 times x2, I need to get something that's no bigger than 5. So that's a constraint, an inequality constraint on the values of x1 and x2. So I could bring the stuff on the left over to the right. So I could write this as 5 minus x1 minus 2x2 is greater than or equal to 0. I just flipped the inequality because I moved everything from the right to the left and left to the right. So I could write it in that form. And what this is saying is now that instead of having a 5 on the right, I now have a 0. So 5 minus x1 minus 2x2 has to be greater than or equal to 0. Fine. Okay, that's just basic algebra. Well, what if we were to define 5 minus x1 minus 2x2 as a new variable s1? And we say, okay, now this new s1 variable, called the slack variable, has to be at least as big as 0. So in other words, it's non-negative. So what this means is the s variable, the slack variable, is determining and showing how much larger, well, how much slack there is between the left-hand side here and the right-hand side. So when I take 5 minus x1 minus 2x2, I get something that's bigger than, or at least as big as 0. If it's 3, okay, then the slack that I need to account for is 3. And that's what my S1 will be doing. So I know this looks a little confusing. How we actually do it, I'll show you, is quite straightforward, but I want to make sure we understand what the purpose of these slack variables are and what they're actually doing. So S1 is defined as this 5 minus x1 minus 2x2. The larger S1 is, the more slack is available in the quantity that's represented by this inequality constraint. So in other words, the bigger the difference is between the right and left sides of the inequality. If S1 happens to be 0, then that means there is no slack. So 5 minus x1 minus 2x2 is equal to 0. So there is no slack that needs to be taken up in the slack variable. Now, this is not actually the way we formulate it. I just want to give you an intuitive sense for how the slack variable is working. What we actually do is we just go straight back to the inequality constraint. X1 plus 2x2 is less than or equal to 5. And we say, fine, if x1 plus 2x2 is no bigger than 5, then I should be able to add in here a slack variable, which takes up that slack between what x1 plus 2x2 actually equals and the 5. So that's what we have here in 621. So x1 plus 2x2 plus s1 is equal to 5. And then s1 is just the difference between x1 plus 2x2 and 5, as we expressed on the previous slide. And then finally, we just have the additional positivity constraint that s has to be non-negative. So s1 is greater than or equal to 0. So that's it. So you can ignore all this in terms of actually doing it. That's just, again, to help us understand get some intuition behind it. But you can just start straight from the inequality constraint, add in a slack variable that takes up the slack plus S1, and that has to be non-negative. So that's your slack variable. So we've introduced a new variable, which we now need to solve for. That's the price you pay for having inequality constraints. Is for each inequality constraint, you have to have another slack variable. Each new slack variable increases the size of the overall system of equations that we need to solve. And that's just the price we pay for inequality constraints. All right, so we are again just taking our inequality constraints and replacing them or converting them into equality constraints and a positivity constraint. So each inequality constraint turns into one equality constraint plus an additional positivity constraint. So one turns into two. There's gonna be lots of remarks today. And again, you're gonna get lost in these remarks. Don't worry about that. Don't force this, just kind of let it come naturally. Try to focus on the big picture for now, and then fill in the details as you go, as you dig more deeply. So we have, again, one additional slack variable for each inequality constraint. And so that increases the total number of variables by one. So if I have 15 inequality constraints, then my design variables, X, is going to include an additional 15 S's, select variables. And this, remember the N, S, and M. So N is the number of unknowns. So that's the number of design variables that we're looking for. M is the number of equality constraints. S is the number of inequality constraints. So S, capital S, is the same as the number of slack variables, little s's, that we're going to need. So when we look at the standard form and the sizes of the various matrices and vectors, they're going to involve these m's, n's, and s's. So we started with n design variables. We add s inequality constraints, and therefore s slack variables. So now the total number of variables is n plus s. So any vector, in this case x, that includes all the variables that need to be solved is going to be of dimension s. Then the slack variables that we introduce for each of our inequality constraints is then added to that list of variables, as I mentioned. The total number of equality constraints, once you're in the standard form, is m plus s. Before you put it in standard form, there are m, Mary, equality constraints, and then you have the additional s, inequality constraints. So you turn those into equality constraints, so you have m plus s equality constraints in the standard form. This will always be less than n plus s. So m is always less than n. Obviously s is the same, but m is always less than n. If they're the same, then you don't have an optimization problem. You get a unique solution for your problem. You go on your merry way, and there's really nothing to optimize. There's only one possible solution. So because m plus s, which is the number of equations, is less than n plus s, which is the number of variables, we say that the system is underdetermined. So if you think way back to when we were solving AU equals B systems of linear algebraic equations, we had three possibilities, right? So we had the situation where we had a unique solution, which was typically what we're looking for in physical cases like the truss problem and so forth. So we had the same number of equations and the same number of variables, and so we could solve for them uniquely and get the unique solution. Or if it's over-determined, that means there's more equations than there are unknowns. So that it's over-determined. There are more equations than I need to get a unique solution. So it's over-determined. Then under-determined is where you have fewer equations than what you need to get a unique solution. That's actually what we would like, what we want in the optimization context, because the optimization is going to then determine which solution, which of the possible feasible solutions that you get from your system of constraints, that's the feasible space, that is the actual optimal solution. So it's underdetermined. And that's exactly what we want in this case. So this is why we actually talk about those different cases when we discuss linear algebra, even for engineers. You know, the mathematicians go on and on about all these different possibilities and cases, and we're kind of thinking, well, all I care about is the case where I have the same number of variables as I do equations. Again, that's true for physical problems, but for non-physical problems like this one, and it's the case, I didn't emphasize this, but you can put the linear regression and polynomial regression problems into a matrix form. Those are underdetermined systems. They're optimization problems. They're underdetermined systems, and we need to be able to solve them. So we need to kind of get away from that thinking of, well, I always want a unique solution. I always need to have the same number of variables and equations. That's not the case in many of these optimization problems in particular. So we have our underdetermined system AX equals B. It includes the constraints. There are an infinity of solutions, possible solutions. That's called the feasible space. So remember, the feasible space includes all of the points that satisfy the constraints without regard for the objective function. So the objective function is what it is. We'll get to that in a moment. But to get the feasible space, we're looking for all the points in the x1 through xn, and now s1 through ss variables that satisfy all of these constraints. All right. So that's where we're headed with all of this. So again, that's the feasible space. And then of those infinity of possible points in the feasible space, because it's a region in our X space. So of the infinity of possible points, we're looking for the one point, there's only one, that also minimizes the objective function. So this is what I talked about on Tuesday with, we draw the feasible space, I'll draw a feasible space in a moment, and then we superimpose lines of constant j. And because this is a linear programming problem, those are straight lines, and they're kind of superimposed on the feasible space. And then we look for, okay, as j increases or decreases, in our case to minimize, where is the point where in the feasible space that has the smallest j? So that's the superposition of the feasible space with the lines of constant objective function j. Siri's going crazy here. You're welcome, Siri. Okay, so in our train car example, let's think about what these variables are, just making this a little more concrete. So we had two design variables. Remember, those were the number of trains. So the number of cars on train 1 was x1, number of cars on train 2 was x2. We had one equality constraint, so m is equal to 1, and s is equal to 2. So that's the number of inequality constraints. And we'll show this again in a moment so you can see it all together, but this we had from Tuesday. So n is 2, m is 1, s is 2. Now we need to convert, for standard form, convert these two inequality constraints into equality constraints. So we'll have m plus s, so we'll have 3 equality constraints with our n is equal to 2 design variables. Now, you'll notice that by introducing these slack variables, we actually don't change the objective function at all because the coefficients of the slack variables are just 0. So when we write down the linear system of equations that corresponds to this optimization problem, the situation will be similar to what we had on Tuesday, but now we'll just have, totally lost my train of thought, we'll have the slack variables introduced along with the design variables. All right, yes, so now I remember what I was saying. So you can add the s's to the objective function. However, the coefficients on them in the objective function will be 0. So adding slack variables changes the clearly my brain has been affected as much as my body with this vaccine. So the cost function or objective function will not change when I add the slack variables. Only the constraints themselves are changed. You'll see that as we do this example. So let's come back to our train car example that we looked at last time, and let's put it into standard form. So last time we didn't bother. It was a simple problem. We only had 2 design variables, and we just kind of motored through it. brute force and we got the two possible solutions and we said, oh yeah, this one has a smaller cost, and so that's the optimal solution. Now let's put it into standard form and solve it more formally. So we have our cost function or objective function, which is the cost of pooling our two trains, 10 cost units times the number of cars x1 plus 15 cost units times the number of cars x2. That's the total cost of pooling our two trains. We have an equality constraint, which is that we want both trains together to pool a total of 100 cars. It could be 1 and 99, it could be 0 and 100, it could be 50 and 50, whatever, but it has to add up to 100. So that's an equality constraint. And then train 1 can only handle no more than 50 cars, so something up to and including 50. X2 has to be less than or equal to 75. So that's the maximum number of cars that each train can pull. And then we also have the positivity constraints, which just say that you can't pull negative cars on your train. So X has to be at least as big as 0, X1, and X2. All right, so that's fine. That's nothing new, just putting it all together again. Our objective function, equality constraints, inequality constraints, and positivity constraint. To put it in standard form, we need to convert our inequality constraints into equality ones using our slack variables. All right, so we have our objective function or cost function that doesn't change. We have our equality constraint, x1 plus x2 is 100. And then x1 has to be less than or equal to 50. So that means there is some slack variable, some value that's positive, s1, that when I add it to x1 is equal to 50. That's how much slack is in the actual number of cars versus the number of cars that the first train could pull. Same thing with x2. So the second car will pull x2 cars, but it could pull x2 plus s2, which is equal to 75. So I don't know yet what s1 and s2 are, but they will be calculated as part of the solution. So I've introduced two additional variables. You'll see down here, my x vector, which was 2-dimensional, is now 4-dimensional because it's n plus s, the number of design variables, which was 2, plus the number of equality constraints, which was also 2. And then we also have, in addition to our new equality constraints from the inequality constraints, we have the positivity constraints on the slack variables. They have to be positive. It's a positive slack because of the way we formulated. All right, so that's our standard form of the linear programming problem. So let's redo our feasible space. This is not going to be any different than it was on Tuesday, but I'm going to express it slightly differently because now we have these slack variables. So we still have x1 and x2, just like before. The feasible space will be the same. So it's to the right of x1 is equal to 0. It's above x2 is equal to 0. Because again, it has to be in the first quadrant. Positivity constraints on the design variables x require it to be in the first quadrant. X is positive and s is positive. And then we have, this is 50. That's the upper limit for x1. And then we have 75, which is the upper limit for x2. So it has to be below that one and to the left of this one. So our feasible space so far is somewhere in that rectangle. Again, just exactly like we had before. But now, in terms of the slack variables, this line at x1 is equal to 50, that's actually corresponding to s1 is equal to 0. If the solution was along that line, then that means it would have x1 cars on the first train, and that would mean there's no slack, there's no s1, it's 0. Same thing at the top here. This one is s2 is equal to 0. So if the number of cars on the second train is 75, then there is no slack, so s2 is equal to 0. Now you'll remember that our original equality constraint added this additional constraint on the feasible space. So this was our points A and B that we had before. So the solution has to be at either A or B. But now what I want to point out, the reason why I drew this, is point A corresponds to when S1 is 0, and point B corresponds to when S2 is equal to 0. And that's always going to be the case. We'll discuss this more in a moment. But at the optimal solution, a certain number of our variables, whether they are design variables or slack variables, a certain number of our variables will have to be 0, because the feasible points are always on the boundaries of our feasible space. They're always in corners, they're always at the ends, in this case, of this line segment that satisfies all of the constraints. All right, so the feasible space looks the same. It's just that it's expressed a little bit differently when we use our slack variables than it was last time when we used our x1 and x2 variables. All right, so that's putting it now into standard form. Now we can put this into a matrix form, because if you look at our system of equations, let's go back here. I have my objective function, and then I have 3 equations. These are all linear equations for x1, x2, s1, and s2. And you'll notice, of course, that I only have 3 equations, but I have 4 variables. And that's what we mean by it being underdetermined. So this is an underdetermined system. There are fewer equations that are necessary than variables to actually get a unique solution. But let's walk through what each of these says. So the first one says that 1 times x1 plus 1 times x2 is equal to 100. So that is our first equality constraint. The second one is 1 times x1 plus 1 times s1 is equal to 50. That is our, what was an inequality constraint that now with the slack variable s1 has been converted into an equality constraint. Same thing with the third equation, x2 plus s2 is 75. So 1 times x2 plus 1 times s2 is equal to 75. Now you notice in this formulation, there's no mention of or inclusion of the objective function. So this just accounts for the constraints so far. All right, so all we've done is reformulate the problem that we had last time into a nice linear algebra system of equations kind of form. We no longer have inequality constraints. They're all equality constraints, which we can write as this ax equals b system of variables, system of equations. So now once we have this in standard form, now this is where things get fun. This is a simple problem. We did it last time, brute force. It's not going to be any more difficult, obviously, doing it this more formal way. So that's why I'm using it to introduce this approach. But things get messy very quickly. So let's just take a look at what we have so far. We have our standard form. I can write that with the slack variables. I can write that as a system of linear algebraic equations. And you might think, well, okay, I've gotten rid of the inequality constraints. So maybe I can just use the same process that we did for nonlinear programming problems. In other words, differentiate the objective or cost function with respect to each of the variables, set them equal to 0, and solve for them using Lagrange multipliers. Unfortunately, that's not possible. And the reason is, remember on Tuesday, I was doing all these hand motions with my flat table surface on different angles. So you have this plane, and that determines the feasible space. And then there's constraints that are like little walls around it. You put a marble in it, and then they roll down to the lowest vertex. So that's a very different kind of scenario than what we discussed in the nonlinear case, where you had some function with minimums and maximums in them, and you just set the derivative equal to 0 that corresponded to the minimums and maximums, and then you found those points. So let's see why this doesn't work here, just in case there's anyone who still thinks that this may be a possibility. So let's go ahead. Let's take our cost function, our objective function, and let's differentiate with respect to x1 and set that equal to 0. All right, we'll slip back and see what that is. So I have 10x1 plus 15x2. So what's the derivative of x1 with respect to x1? Well, it's 10. Okay. So that says that 10 has to equal to 0. Well, that's obviously not true. Likewise, differentiate with respect to x2, and you get 15 is equal to 0. So clearly, that's not getting us anywhere helpful at all. And again, the reason is because we do not have a traditional function which has minima and maxima in the traditional sense. We need constraints. Constraints are absolutely necessary and integral to, no pun intended, because I don't mean integration in a mathematical sense, integral to these linear programming problems. All right, so we have to throw that out. That's not going to work. Once again, that's because the extrema are actually at infinity, which is why we need these bumpers in order to keep it within a finite range. Did someone have a question? I saw a hand up that went down. Are they just playing with the...
Yeah, you basically said exactly what I was about to ask.
Okay, great. I'm a mind reader. That part of my brain is still working. Sorry to say, because that's kind of scary. Don't tell my wife that I'm a mind reader, that is. Thanks. All right. So this leads us to what's called the simplex method. So this is the algorithm. The simplex method is an algorithm. It's very complex. Like I said, if you look at the actual codes, of which there are ones available in MATLAB, in Python, and various kinds of packages out there, you do not want to have to write this yourself. These are highly complex, very detailed codes. There's a lot of possible situations that can arise that you need to be able to account for and adjust for as necessary. So again, I just want to give you a kind of an overview, enough detail that you understand how it basically works, and enough detail that when you use one, it makes sense to you what it's doing, but not so much detail that we get further into the weeds than we really want. Okay, so let's discuss the simplex method. So let's come back to our standard form, and that'll be our starting point. So as always, we have the original word problem. We write the word problem into mathematical form with objective functions, inequality constraints, equality constraints, positivity constraints. Then we adjust everything so that it truly is a minimization problem. We adjust the equality constraints, or the inequality constraints using slack variables so that they're all equality constraints. And we make sure that all the positivity constraints are just that, they start at 0. And so you put it into the standard form. We'll do more examples of that, so you'll see that. And then we want to be able to write this in matrix form. So far I've been kind of avoiding hinting at, suggesting the matrix form, AX equals B specifically, but now I'm going to use the vector matrix form to formulate these, because then that'll allow us to just get whatever size is necessary. So the objective function, J, is the unit product of C with X. The C's are the C1, C2 through C cap N coefficients in the linear objective function, which involves X1, X2 through X cap N. So inner product of C with X, which is the same as C transpose times X. Fine. The equality constraints, just like we did before, we're going to write as a system of equations, AX equals B. So these are all the equality constraints. There's M equations, which is the number of equality constraints. We have S additional equations because of the conversion of the inequality to equality constraints using the slack variables. So that is our AX equals B. So we're not trying to solve AX equals B like we were earlier in the semester, but AX equals B is the encapsulation of all of the constraints that we have on our problem, on all of our variables. And then we have our positivity constraints. We have capital N design variables and capital S slack variables. So there are N plus S positivity constraints. Our variables then are, again, N plus S, all the X's and all the S's. Now, in terms of sizes, the size of A, the matrix in our equality constraints, we have M plus S equations and N plus S variables. Once again, M is always less than N, so it's an underdetermined system. B is M plus S by 1. So the right-hand side vector, we had originally M equality constraints, we've added an additional S equality constraints from the inequality constraints. And so now B is N plus S. I told you it's going to be confusing. And this is the whole key. Let me put exclamation points all over the place here. This is the whole key. And I've been mentioning this. I've been doing my little hand motions for this, but this is the whole key to the simplex method. And that is that it recognizes that an extremum, in other words, the optimal solution that we're looking for of a linear function, has to occur at the corner points of the feasible space. So again, this is my table, my flat surface, whatever orientation it happens to be. The marbles all roll down. So they're going to roll down into the vertex, the corner that is the lowest. That corner is defined by the various constraints. So every corner of, if it's two-dimensional, it's a polygon. So every corner of my polygon is a potential optimal solution. It's in the feasible space. And I just have to determine the one point, the one vertex, the one corner that corresponds indeed to the optimal solution. So everything is based on that fact. So now, oh, I told you, I warned you. So now these corner points, so we have the feasible solution, which is a region, which has an infinity of points. The basic feasible solution is going to be all the corner points in the feasible solution that could be, they're not necessarily, but they could be their potential, their candidate optimal solutions. The one that has the smallest value of the objective function, well, that's the optimal solution that we're looking for. So of all of those vertices in our polygon, we want to evaluate the values of J, like we did for our train car problem last time. We only had two. And we want to find the one, determine the one that has the smallest value of J, minimum value of J. That's our optimal solution. All right, so just to think about this. So we have the feasible space, which is a infinite number of points bounded by our constraints. The corners of the feasible space form a polygon. At least we hope so. Again, we don't want openings where things can spill out, marbles can roll out. So if it's a closed space, like it needs to be for a well-posed, well-formulated optimization problem, then the corners of the feasible space are the basic feasible solutions. And then the one of those corners that corresponds to the smallest J, that is the optimal solution. Makes perfect sense, right? It actually does. It's just very confusing because of all the terminology. All right, so that's the way we need to think about it. Feasible solution, feasible points, basic feasible points, and then the optimal solution itself. Okay, now because the minimum that we're looking for is at one of these corners, I don't have to check every point within the feasible space. There's an infinity of them. I only need to check these corner points. And in the previous example, there were only two. That was not a problem. I could do it using brute force. Once again, what if there's more, there's lots, then things can get out of hand very quickly, as I'll illustrate in a moment. But this simplifies the linear programming problem significantly. Rather than looking at every point in the feasible space, I'm just looking at the corners of the polygon that bounds my feasible space. All right. This can get pretty out of hand pretty quickly, as I said, very tedious. Here, I'm not going to derive this, but this is the number of possible basic feasible solutions. In other words, this is the number of vertices or corners in my feasible space. If I have n plus s variables and m plus s equality constraints, this is the number, and these exclamation points, of course, are factorials. So this is the number of possible points that I would need to check in a brute force way, unless you think, well, that can't be so bad. Well, let's just take a modest n as 20. So 20 design variables, 5 equality constraints, and only 5 inequality constraints. That doesn't seem too bad, right? That should be pretty manageable. Well, if you stick that in, turns out that that's 3.2 million possible basic feasible solutions. So I'm not going to sit here and check. I don't have the patience to sit and check every single one of those possible basic feasible solutions to see which one has the smallest j. So that's not going to work. Again, we need a more algorithmic step-by-step process that gets me to the optimal solution. All right, so that's where the simplex method comes in. And it specifies a step-by-step procedure. So it is just an algorithm. It's a computer algorithm, very complex, but nevertheless, it's a step-by-step procedure. It progresses through the basic feasible solutions. In other words, again, the corner points, in such a way that each time you go from one point to the next, it's going to decrease the value of the objective function. So there's really two questions that the simplex method has to answer. Which point do I start at? Which of my corner points, basic feasible solutions, do I start at? Okay, I pick one. I calculate the j, and then I decide, well, do I want to go to the left or do I want to go to the right? Which direction should I go? So those are the two basic solutions, which sound very simple. But of course, in order to cover every possible scenario and every possible situation, it gets quite complicated. And so you start with a point, you calculate j, and you ask yourself, well, if I go to the left or the right, which of the neighboring vertices gives me a smaller j? I don't want to increase the j because I want to find the minimum j. So I want to find the one that decreases j, because presumably that's in the direction of the vertex that's going to give me the optimal solution based on these superimposed lines of constant j. This is one of the nice things about linear programming is lines of constant j literally are just lines. They're straight lines. So there's not a situation where you could be going left and then it kind of fakes you out and says, oh, no, you should have gone right. So that's not going to happen. All right, so figure out where to start, which corner point to start at, and then which direction to go in order to decrease the value of the objective function. And then you just keep going until it doesn't decrease anymore, and that is your optimal solution. That's your minimum. So we can put this into a formal mathematical form, a matrix form, vector matrix form called a
Sorry, I'm having trouble hearing you.
Yeah, I know. So we call this the Simplex Tableau. Tableau is just a fancy French term for table. And so this looks like a table. In fact, I will write it as a table in a moment, but we can also write it in matrix form. And it looks like this. This is the general form. So remember, we had our objective function, which was j is equal to c transpose times x. And then we had our constraints, which were ax equals b. So if we combine them into one single system of algebraic equations, we get this. So we have 1 times j minus the transpose of c, x times x, that's the inner product of c with x, and that's equal to 0. That is our objective function. That's the vector form of our objective function. And then the constraints are 0 times j, because j does not come into the constraints at all, plus a times x is equal to b. So ax equals b, those are all the constraints. So all we've done is combined all the constraints and the objective function into one system of linear algebraic equations. You'll notice that this 0, for example, is bold, so that's a matrix. It's actually a vector, sorry, it's a vector of the same size as b. This 0 is not bold, that's just a scalar, because the first equation for j is a scalar equation. So that's all correct in terms of the bolds and the not bolds. 1 is not bold because that's just 1 times the scalar function j. All right, so when you unravel that, you get your objective function and you get your ax equals b constraints. Okay, now I'm gonna just load on the n's, and the s's, and just so we can see how all these things come together. So again, just kind of follow along, keep your head above water, and then we can go back and sort out the details. So the vector c has as many elements as x. X includes all the design variables, and it includes all of the slack variables. Now remember, in C, the coefficients of the slack variables are all 0. So I'm not changing j. It's still the same inner product of c with x. However, we are, in order for all the sizes to work out consistently, we're going to make x, and therefore c, n plus s, so that the sizes are all the same. All right, but again, the coefficients are all just 0. Then a, so the matrix in ax equals b, the equality constraints is m plus s, so that's the number of rows, that's the number of equations, by n plus s, that's the number of columns, or the number of unknowns, which is the design variables plus the slack variables. Correspondingly, b is m plus s by 1, which of course it has to be for the sizes to work out. It's m plus s by 1. It's the same size as x. No, sorry, same size as the number of rows of A. Phew, that was close. I said this before, so the 0 here on the left, that is actually a vector. It's an m plus s by 1 vector. It's the same size as b, whereas on the right, the 0 is just a scalar, just to make sure that that's all clear. So we have m plus s plus 1 equations, yikes. So where do these all come from? M equality constraints plus s inequality constraints plus 1 objective function. So m plus s plus 1. The number of variables is the original number of design variables, n, plus the number of slack variables, s, plus j, of which there's only 1. And once again, this is an underdetermined system because n is always bigger than m. If it's not, then we do not have an optimization problem. If it's the same, you can get a unique solution. There is no room for optimization. If it's less than, then it's overdetermined and there is no solution. So we're looking at the situation where n is bigger than m. There are more design variables than there are original equality constraints. Confused yet? All right, so we can augment the simplex tableau that we had a moment ago with that first equation for j. So before I just had 3 by 4, well, not that one, sorry, 1, 2, 3, 4 for these variables. Now I'm including an additional column and an additional row in A, not in A, sorry, it's the simplex tableau, an additional variable j that we're solving for, and then the corresponding element in the B vector that goes along with that. So these three look familiar. Those are the constraints. This one is the objective function. So 1 times j minus 10 times x1 minus 15 times x2 plus 0 times s1 plus 0 times s2. Again, the coefficients on the s's are always 0, and that's equal to 0. That's your objective function. So the simplex tableau pulls together all of the constraints, which what was inequality constraints, which are now equality constraints, which the original equality constraints. Boy, if I can't even say it, obviously we've got bigger problems. All right, and then plus the objective function for j. We can put this in a little bit tamer looking form, just as a table. So you'll notice the labels on each column is the j's, the x's, the s's, and the b's. The values here are the same as what we have up here. So this is the formal matrix version, linear algebra version, ax equals b. Sorry, not ax equals b, I keep saying that. It's the ax equals b augmented with the objective function. And this is putting it in a more tabular form like you would write on paper. It's not a formal mathematical form, but they're saying exactly the same thing. One thing you'll notice is these simplex tableaus are usually quite sparse. And again, sparse means lots of zeros. So when you write it down in matrix form, there's zeros all over the place. And the bigger these problems get, typically the more sparse they get. And so one of the things that we get into in computational linear algebra, numerical linear algebra, which is beyond the scope of our considerations, is how do you efficiently solve very large systems of equations that are sparse, that have lots of zero values in them. So you could think, well, like in this case, I don't have to do anything as far as Gauss elimination on these. I could just Gauss eliminate this one, Gauss eliminate this one, and go on my merry way. Well, so that's one approach. It's not the most efficient, but that's one approach. The idea is, again, I can hopefully take advantage of the sparsity to speed up the solution. But that's something we're not going to worry about. We'll let the mathematicians, the computational mathematicians, worry about that. All right, so here are the guiding principles. So these are the things that guide the simplex method. These are the things that guide the step-by-step process encapsulated in the simplex method. This is not the full-blown algorithm. This is not every detail of the algorithm. It's the guiding principles. It's the things that we need to understand as engineers in order to help us better understand how to use these tools. Okay, so I've got 3 guiding principles. All right, first of all, because the optimal solution occurs at one of the extremes, in other words, one of the corners, then the value of n plus s minus m plus s, which of course is just n minus m, of the design variables or the slack variables must be 0 for the final optimal solution. Oh my goodness, what is he saying? These are called non-basic variables. The remaining ones are called, I told you last time, there's lots of jargon. So in other words, at each corner, you have all of your design variables and all of your slack variables, and they each have a value at each corner of the feasible space. The point here is that we know ahead of time that a certain number of those variables is going to be 0 at a given vertex, at a given corner. It won't be the same variables at each corner, but at each corner, there will be a certain number, a known number of variables that are 0. So let's walk through this. If there are 3 more variables than equations, so again, it's underdetermined. So n minus m is 3. So 3 more variables than equations. Then then 3 of the variables must be 0. In other words, when you get to that feasible point, their values have to be 0. In other words, they're hitting up against their positivity constraints. So just think of our rectangular feasible space in the train car problem. So at each corner, 2 of the x's and s's are 0. At the origin, x1 and x2 are 0. At, that was A, right? B, at B, x2 is 0 and s1 is 0. And then at the top right corner, I guess that was C, then S1 and S2 are 0. And then at the 4th point, A, B, C, D, yes, I can count, is then X1 is equal to 0 and S2 is equal to 0. So at every point, 2 of the 4 variables equals 0. And the key then is determine which ones are which. So the subset of points that are 0, those are called the non-basic variables. The remaining non-zero variables are called the basic variables. This is confusing because you think non is the variables, non-zero, so sorry, 0 is non, and non-zero is basic. So it's kind of backwards from what you think just from the terminology. In any case, the 0 variables are in the non-basic group, and the non-zero variables are in the basic group. So we just have to figure out, as we go around our basic feasible points at each of these vertices of our polygon, which of the variables, x and s variables, are in the non-basic and which are in the basic variable subsets. That's essentially what we're trying to figure out. All right, so again, we then have a step-by-step method for determining which variables go into each of these buckets in order to determine which one gives us the optimal solution, which of course corresponds to the minimum value of the objective function. Once again, we could do this in a brute force way. So all I've said so far is, well, I know 2 of them are 0 or whatever number of them are 0, fine. I can take advantage of that in getting the j for each point, but that's still a brute force approach that doesn't help me very much. So with the non-basic variables set to 0 then, we can get a unique solution for that particular point, that particular basic feasible point. And then we can see which one, again, as we go around, does the j decrease or increase? Are we getting closer or farther away from the optimal solution? All right, so let's see how this goes for the train car example. So we're just going to apply those principles to the train car example. This is not exactly the simplex method in the way that it would be implemented on a computer. This is kind of a heuristic or a intuitive application of the simplex method based on those three principles. All right, so let's go back, rewrite the standard form, which is right here, same as we had before. So the first equation is the objective function. The next three are the equality constraints. One was originally an equality constraint. Two were inequality constraints and now have been made equality constraints using these slack variables, S1 and S2. You can see on the right-hand side, 100, of course, corresponds to the total number of cars. 50 corresponds to the maximum number of cars on the first train, and 75 corresponds to the maximum number of cars on the second train. Now, in this case, n minus m is 1. So n is 4, m is 3, or if you include the first row, then n is 5 and m is 4. But either way, n minus m is 1. And so there is one variable that's in the non-basic set. So that means there's going to be one variable that's not equal to 0. Sorry, that will be equal to 0. Sorry, I fell for the trap. There's going to be one variable that is in the non-basic set, which means that those will be equal to, well, that one will be equal to 0. The remaining 4 variables will be in the basic set, and those are then non-zero. So once again, we just need, I make it sound simple, we simply need to, it's in no way simple, I should put that in quotes, we simply need to determine which of the design and slack variables lie in the basic and non-basic subsets of the solution for that corresponds to the optimal solution. Sounds simple, it's not so simple, obviously. All right, now in this case, there were 2 possible scenarios, A and B. So our basic feasible set involves 2 points, A and B. Point A corresponded to S2 is equal to 0, and point B corresponded to S1 is equal to 0. If you go back here, so A, oh, I got them backwards. Oops. So this one is A, my bad. This one is B. So A corresponds to S2 is 0, B corresponds to S1 is 0. All right, so let's take a look at each of those cases in light of the guiding principles that we just outlined. All right, so point A corresponds to S2 is equal to 0. Point B corresponds to S1 is equal to 0. Let's see what that means. Let's look at each point one by one. So let's look at point A, which is on the top there where S2 is equal to 0. And what we'll do is we'll separate out the non-basic variable, which in this case is S2, because that's equal to 0, from the basic variables, which are the non-zero ones, which is x1, x2, and s1. So now look what you have. You have this matrix, which is now 4 by 4, plus this matrix problem, which is 4 by 1, but S2 is equal to 0, so this whole thing just goes away, is equal to this 4 by 1 matrix. Well, guess what? Now we have 4 unknowns, 4 unknowns and 4 equations, so we can get a unique solution. If you write this in matrix form, we'll call this, let me label it, we'll call this A sub B for the basic variables, XB, which includes the basic variables, AN, which includes the non-basic variables, and S2, which includes the non-basic variables. Sorry, I think I said AN was the non-basic variables. It's the coefficients of the non-basic variables. All right, so this term goes away because S2 is equal to 0. So we just have AB times XB is equal to B. That's a lot of B's. That, once again, is now a system of equations where we have the same number of equations as we do unknowns. We can solve that for unique solution for the J, X1, X2, S1 variables that we have. And then we're done. Let's look at point B. Oh no, let's look at the solution first. So if we solve this, we get the inverse of AB. So inverse of AB times B. Then that gives that J is 1375, X1 is 25, X2 is 75, and S1 is 25. Notice what S1 is. It's the slack variable for X1. So 25 plus 25, of course, is 50, which is the maximum number of cars that the first train can pull. So this corresponds to, it gives us everything we want to know. We know the value of the cost functional, it's 1375 cost units. We know the number of cars on the first and second train, and we even know, we don't really care about it, but we even know the value of the slack variables that are non-zero, 25. Great. So there's our 1375, which we've seen before. For point B, so this is on the right vertical boundary, where S1 is equal to 0. So if we separate out the non-basic variables, which in this case is S1, because it's S1 that's 0, from the basic variables, which are now X1, X2, and S2, then we get this. It looks similar to before, but now you notice we have J, X1, X2, S2 instead of S1. And now S1, we've taken out separately because that is equal to 0, so that this whole thing goes away. And we now have a 4x4 system of equations that we can solve once again to get the unique solution for J, X1, X2, and now S2, because it's S1 that's equal to 0. When we solve that, get the inverse of AB, multiply times the vector B, and this is what we get. So the cost is 1250. The number of cars on the first train is 50. The number of cars on the second train is 50. And the slack, S2, for the second train is 25. Because remember, it had a maximum limit of 75. So 50 plus the slack variable 25 gives us the total that it could have pulled, excuse me. All right. This, again, looks familiar, 1250. That's obviously smaller than 1375. And so point B corresponds to the minimum solution. Now, again, I've used somewhat of a brute force approach. I have not looked at all the possible situations here, and I only had 2 possible feasible solutions. So this has been still a very simplified problem in that respect. But I just want to put it, the same problem, so there's nothing new about the problem, into the context of first the standard form, which we did earlier in class today, and then now the Simplex Tableau, which we've now done, and then recognizing the basic and non-basic variables for each of the possible optimal solutions to determine which one is indeed the optimal solution. All right, some comments. So these are the general steps. I've mentioned these before, but I want to put them all in one place so you can see them all together. So we start out with our linear programming problem, the optimization problem as it's formulated in the word problem. We write it down, and then we need to convert it to its standard form. So the things that put it in its standard form are, first, you need to be sure that the objective function is truly a minimization problem and not a maximization problem. As we've said before, if it is naturally posed as a maximization problem, so for example, if the problem is to maximize the profit of a company, then all you have to do is take minus J, because the minimum of a maximum is a maximum of a minimum. That's not the right way to say it. The maximum of a function is the minimum of the negative of that function. We also need to convert our inequality constraints. If you have any that are greater than or equal to, then we need to convert them to less than or equal to, again, simply by multiplying by -1, because multiplying both sides of an equation by -1 flips the inequality. So make any maximizations, minimizations for the objective function. The inequality constraints, convert them from greater than or equal to less than or equal to, so that they're all standard. And then finally introduce any slack variables that are necessary in order to convert your inequality constraints into equality constraints. Once you've done those steps, you now have the standard form. All right, so again, word problem, raw equations based on the word problem itself, adjustments to put it into its standard form, And now we're ready to apply the simplex method. So the next step then is to write down the simplex tableau from that standard form, determine which of the basic feasible solutions you're going to start with being 0. So which point are you going to start at? That determines which values of x and s, the x's and the s's, which ones are 0 and which ones are non-zero. So that determines your starting point. And then you'll proceed from one basic feasible solution to the next. You'll go in order to determine, again, the direction, which is decreasing the value of j, in order to get closer and closer and closer as you go around these points, these vertices, to the one that corresponds to the optimal solution, which with the smallest value of j. Now at each step, you're basically moving in and out of the basic and non-basic variable sets of variables. So every time you go from one vertex to another, you're exchanging one of the variables that was 0 for now another variable, which is now 0. So the other one's not anymore and a new one is. So basically, as you go from point to point, the big question is that you have to answer, the simplex method has to answer is, which variable goes into the basic set and which one comes out? And that's what we really need to think about. I do have another example here to pull this all together. I don't think I want to start this because we won't get done with it. You can start problem set number 6 if you'd like on optimization. Obviously, I have more to say on the simplex method, so leave that problem for later, but all of the other ones on nonlinear optimization, constrained and unconstrained optimization, you can do all of those. So I would start on those. This will be due a week from tomorrow. So what is that? I think that's April something or other. Oh, and I need to put it up on, yeah, so April 2nd, next Friday, and I need to put it up on Blackboard. Just realized I hadn't done that yet. All right, so you can get started on those, but again, we'll talk more about the simplex method. We'll do another example next time to kind of pull this all together. All right, are there any questions? All right, so I'll see you on Tuesday. And in the meantime, I'll post problem set 6. And yeah, you're good to go.
I had a question, Professor.
Sure, go ahead.
Earlier in the notes, you said that from the example we were doing with the train cars that we had one variable in the non-basic set and then 4 in the basic. Did you mean to say 3 in the basic set?
I may have. I should. Okay, so yeah, here's where it gets a little bit confusing. So, and you maybe saw that I was kind of tripping around about this. Let me show you. So in this form, no, not that form. In this form right here, the question is whether you include this as one of your equations and this is one of your variables. So now in the simplex tableau, I am, but j is always non-zero. J will never be 0. So in terms of the number of variables in the basic set and non-basic set, it's only going to be one or more of these variables, not including j. However, if you write it in this form, there are 1, 2, 3, 4, 5 unknowns rather than 4. So that's why sometimes I may have one or more, I may say it with one or more than may seem correct based on what I've said before. And that's because I include j or not. In the end, I should try to be consistent. I apologize for that. But in the end, it doesn't matter because the j is always non-zero. J is never part of the basic set where you have, sorry, non-basic set where you have 0 variables. So when you're looking at which ones come in and out of these 2 sets, it'll never include j. So whether you include j or not really doesn't matter. But yeah, you saw that I kind of tripped up on that right here. Because n in the original problem was 2. M in the original problem was 1. And then S was 2. And so my n minus m, I said was 1, because n is 2, m is 1. And so n minus m is 1. but it looks like when I include this additional equation here, it looks like it's actually 2. So that I need to, sorry, be more explicit about that. You can include it or not include it. Here it looks like you should, because otherwise you're talking about the wrong numbers of variables. But again, it's always non-zero, so it's never moving from the basic to non-basic set, or vice versa. Sorry about that. Yeah, thanks for bringing that up.
That makes sense. Thanks.
Professor, when will you be posting problem set 5?
Oh, did I miss 5? Am I off by 1? Yeah, I'm off by 1. You're right. So yeah, sorry to scare you there. So I consolidated 2 into 1, and I did not change the slides because I didn't want to confuse you with the slides, but you're right. We're on problem set number 5. Sorry about that. So this one will be 5, not 6. Sorry. Thanks.
Okay, thank you.
Yeah, thank you. All right, so see you guys on Tuesday. Have a good weekend and enjoy the new look Bulls. For you Bulls fans, some big trades today. So hopefully that will result in some exciting play and lots of wins. All right, see you guys.